Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty and today we will discuss about the reversed Carnot cycle. Already we have discussed the Carnot cycle in details and all of us know that the Carnot cycle is the most ideal cycle for the heat engines, and all the processes of a Carnot cycle can be reversed. The reversed Carnot cycle is the most ideal cycle for both refrigerator and heat pump. So before discussing the reversed Carnot cycle, we should know what is the function of heat pump and then what is the function of a refrigerator. The function of a heat pump is to maintain the body at a temperature higher than the atmospheric temperature. And as far as the refrigerator is concerned, the function of a refrigerator is to maintain a body at a temperature lower than the atmospheric temperature. But as far as the cycle of operation is concerned, that is same for both heat pump as well as the refrigerator. Now, we will consider the PV and TS diagram of the reversed Carnot cycle. This is the TS diagram. So from the PV and TS diagram itself, you can make out that two of the processes are reversible adiabatic or isentropic processes, and two of the processes are reversible isothermal processes. The same is true about the Carnot cycle also, but here it is just carried out in the reverse direction. So the processes are 1, 2, 2, 3, 3, 4 and 4, 1. 1, 2 is a reversible adiabatic compression process. Two, 3 is reversible isothermal compression process. 3, 4 is reversible adiabatic expansion process, and 4, 1 is reversible isothermal expansion process. Now, in process 4, 1, heat is actually extracted. You can denote this as QE, and here heat is actually delivered. And both in heat pump as well as refrigerator, the working substance is refrigerant, and the refrigerant actually absorbs heat from the space or body which is to be maintained at low temperature, and in this process 2, 3, this is to be delivered to the surrounding medium or the medium which is to be maintained at higher temperature. Now, already I have told you that there is no difference as far as the operations are concerned, but they are carried out just in the reverse direction in which actually the Carnot cycle operates. And we know that when a system is undergoing a cyclic process, W net is equal to Q net. So now the net work transfer W net is equal to difference between the heat that is delivered to the surrounding condensing medium minus the heat that is extracted from the medium which is to be maintained at low temperature. So that is equal to, let this temperature be TH, the higher temperature, and this be your TL, TH and TL. And here deliberately I am using temperature TH and TL because temperature corresponding to point 2 is same as temperature corresponding to point 3, and temperature corresponding to point 1 is same as temperature corresponding to point 4. So to avoid that confusion, I am using TH and TL. So QD will be equal to TH multiplied by difference in entropy, that is S2 minus S3, and as far as QE is concerned, that is the heat extracted, that is lower temperature which is constant, that is TL, multiplied by S1 minus S4. As 1, 2 and 3, 4 are isentropic processes, you can represent this as TH multiplied by S2 minus S3 minus TL multiplied by S2 minus S3. So what we have done, we have substituted S1 by S2 and S4 by S3. So that is equal to TH minus TL multiplied by S2 minus S3. Next thing that we have to find out the performance parameter of the reversed Carnot cycle. Unlike the heat engine, where the performance parameter is eta, here we have to use a different notation for the performance parameter, because the performance parameter will not be a single one. It will be COP for refrigerator and EPR for the heat pump. And the performance parameter is depending upon these two factors, whether we are considering this for a refrigerator or whether we are considering it for heat pump. Now, when you are talking about the performance parameter, first we take into consideration the desired effect. In case of efficiency, it is the ratio of W net divided by the heat supply. Because in that case, this is our objective. Our objective is to get W net amount of work output, and for that this is to be supplied. But when it comes to your refrigerator, the desired effect is extraction of QE amount of heat from the body, which is to be maintained at low temperature. We use the notation COP, which represents the coefficient of performance, COP of the refrigerator. Here the desired effect is extraction of heat divided by W net. This is the amount of work that is to be spent upon the system in order to extract heat from the body, which is to be maintained at low temperature. So that will be equal to QE, as you all know, is TL multiplied by S2 minus S3. Then what is W net? Already W net is TH minus TL multiplied by S2 minus S3, and you get it as TL divided by TH minus TL. So the COP of a refrigerator working on reversed Carnot cycle is the ratio between the lower temperature divided by difference between higher and lower temperature. So this is for a refrigerator. But when you are talking about a heat pump, our objective is different. Here our objective is to maintain a body at a temperature higher than the atmospheric temperature. So we usually use the notation EPR, or the energy performance ratio, for a heat pump. EPR. Some of the professors, they do also use the term COP, but they do mention it as heat pump. Otherwise, there would be confusion between the COP of refrigerator and COP of heat pump. So here, what is the desired effect? Desired effect is delivery of QD amount of heat to the body, which is to be maintained at high temperature, divided by W net. That is equal to QD divided by Q net, that is equal to TH, that is the constant temperature that is maintained, multiplied by divided by TH minus TL multiplied by S2 minus S3, that is TH divided by TH minus TL. So that actually represents the performance parameter of the heat pump, which is known as your energy performance ratio or COP of the heat pump. Another thing that I would like to tell you, that don't get confused when I am computing the Q net. There is a fundamental difference between the heat engine and the heat pump and refrigerator. Because in case of your heat engine, our objective is to get work output. So there, actually we get work output from the system. But in this case, actually work is spent upon the system. So while computing the net work output or net heat input, we do not follow the same process, because in that case the heat that is supplied and the heat that is extracted will not be exactly same, because in this case the heat that is to be extracted will be of lower value and the heat that is to be delivered will be of higher value, because the heat delivered is the summation of heat extracted plus work done. Because in this case, particularly when it comes to refrigerator and heat pump, work is spent upon the system. Whereas when we are considering the heat engine, we obtain work from the heat engine. So the heat that is to be delivered to the working substance will be more than the heat that is coming out. So there should not be any confusion as regards to this, and I sincerely believe that your concept about the reversed Carnot cycle as well as the performance parameter, that is EPR for heat pump and COP for refrigerator, would be crystal clear. If you have any doubt related to this lecture, please do put questions so that I will try to answer. I would request you to subscribe to my channel if you have not done so, and please don't forget to like and comment on my video. Thank you very much for your cooperation. Hope to see you soon for another lecture on my YouTube channel Erudispace.